Foundation Models for Decision-Making Agents, Part 19. I'm discussing a presentation by Xiao. He gave that at CVPR 24, and it's about foundation models for robotics, actually. So this fits really nicely into my series. Ted has an interesting blog post that came out about 6 months ago, or even more, almost maybe three-quarters of a year ago, uh, where he talks about the massive advancements that robotics made in 2023. It's a little bit before I started my foundation models for decision-making agents, for embodied decision-making agents series. But I think what I find interesting about Ted is we're definitely on the same wavelength here. I think we're both very excited about the application of foundation models for robotics. That's in essence our parallel. I think he's also the one who inspired me to think about transfer learning. I mentioned that in my most important takeaways from CVPR actually was one of his presentations where he talked about the transfer learning of robotics, that which means that you can train a robot to do a pickup of a pen, you can train a robot to pick up a bottle, you can train a robot to pick up a broom. But if you are able to create a foundation model where you can train all these things together and then have the robot execute those tasks, the performance will be better even on specific tasks relative to robots that have been only trained specifically. So there is a generalization and transfer learning, and the idea is that that's because of navigation. So fundamentally, robotics is the problem of navigation, and um, and foundation models can help that because you can, in principle, solve the navigation problem by tokenizing spatial information and action information. This is roughly, I think, the way I understand this presentation, and I think that's why we have all the other benefits that come with foundation models, which is data scaling. Ted talks about the need to uh, solve a few problems on the go. I mean, one is data collection, one is model architectures, and then evaluation. So those are the three big problems that need to be solved. So let me get this clear, just to be perfectly crystal clear here. The idea of foundation models for decision-making agents, excuse me, for embodied decision-making agents, this idea is certainly interesting. Now, and the reason we're inspired by this is because we've seen it with large language models. So we've seen it with text, and we've already seen it, excuse me, with some of the robotics ideas such as PaLM at DeepMind, where Xiao works. So we've already seen it. We've also seen it with Tesla and FSD. Also, although Tesla doesn't talk about it as much anymore, Tesla is kind of quiet. And we're also expecting to see it with the Optimus robot. So we're seeing transfer learning and generalization. Now, if we want to go down that route, we have to solve a couple of fundamental problems. One is, let's think about what it actually means to build a foundation model for embodied decision-making agents. And then what kind of data do we collect, and then how do we evaluate? So let's go step by step. So what is it? What does it actually mean to build a foundation model? Well, at a big picture scale, what we're going to do is we're going to tokenize, right? I mean, this is how they work. This is how the models work in the language space. So we go from word to vec, and then we run these vectors through a transformer architecture, and that's how we get GPT. So how can we do the same with robots? Like, what's the equivalent here? And I think I want to start with the end. I want to start with I think with the conclusion, which is that robotics is a navigation problem. I think this is probably the single most important takeaway I got from CVPR. So robotics is a navigation problem in the sense that we are trying to find a trajectory through space, and now we can use foundation models for that. We can also use other things like reinforcement learning and stuff, but let's just focus on foundation models for a second. Let's just try to understand what that actually means. So we have we have an object, and that needs to be picked up by the robot. So the robot has to find a way to get to the object and then put it somewhere. In very simple terms, this is the problem. And the way this can be solved is by tokenizing spatial information and action information. And this is exactly what Ted is suggesting. So it's space to vec and action to vec. Turn everything into strings of numbers and then run it through a transformer and see what you get, right? This is roughly the way he sees that the foundation models for embodied decision-making agents landscape. Okay, so I think we agree with that. We don't have a lot more input right now when it comes to this particular type of problem setting. Now let's talk about the data collection. Okay, so let's say we have a consensus on the architecture. How do we collect data? It sounds so typical AI, 2024. It's about the data. It's about the data. Well, it is about the data, because the question is, look, we can have the best model in the world. If we don't collect the right data, the most efficient type of data, it's not going to work. By the way, there's a chinchilla efficiency metric also, which I forgot to mention in the model architecture, and it's kind of combined with the data, right? We want to optimize for data size, we want to optimize for parameter size, and we want to optimize for layer depth and width of models. So we want to find an optimal number for all these things, so that they can get us better performance. Now let's talk about the data. So if we want to train a robot to pick up a bottle and then be able to generalize from picking up a bottle to picking up a pen, and then generalize from picking up a bottle and put it on a table to picking up a bottle and put it on a shelf to picking up a pen and put it on top of the shelf or below the shelf. So if we want to be able to generalize in that way, we also want to be able to train the model in a certain way. So do we have to train the model to do all these specific tasks, or can it generalize? Can it understand what it means to be on top of something? And it doesn't matter what that something is. So those are the kinds of questions that Ted is asking that I find fascinating, and the answers are still relatively open in the wild. But let's get back to the navigation problem. If we can extrapolate from GPT and what it's able to do with text to a robotics foundation model, then I think if we tokenize properly, and tokenization is very key. Remember Karpati's video on that. So even in the language model space, tokenization is a not yet solved problem. We're there, but it's not fully solved. So what is the right way to tokenize a navigation problem is not 100% clear. But let's assume we find a way, then we should, in principle, be able to generalize from on top of a table to on top of a shelf to on top of something to on top of on top of on top of something, and so on and so forth. Because there is a certain semantic understanding of the concept of being on top of something, which comes from the transformer architecture, the the cross-attention, self-attention, and all of these kinds of things that the transformer architecture brings to the table. So, but again, we haven't really understood fully what the best data strategy is. There's a lot of work, RT1, RT2, RTX, RT1 being, these are all Google and DeepMind projects. There's other stuff out there. NVIDIA's doing a lot of work. So these are real world robots that are trained on real tasks, and then different labs combine the data sets, and RTX being that we train a robot to pick up stuff in one lab and then have other labs evaluate that, their robots on the model that was trained in the lab over there, with different embodiments on different tasks. So, generalized tasks. So you tell me that you were able to pick up a bottle in lab A and put it on the table? How about in lab B, can we pick up a pen and put it on the table? So those are the sort of evaluations that are being done right now, and RTX being sort of the really, I would say, the frontier model, at least as we speak today in the middle of 2024. This brings me to the evaluation question, another thing that Ted raises, very, very important point. What is evaluation? Okay, AGI is a bad problem because it's not clear how to evaluate it. So let's not even go there. That's what I find so fascinating about people like Ilya Sutskever, who, according to Chris Ray, deserves a field medal, but he's not smart enough to understand that building AGI is stupid. It's stupid because we don't even know what it is. So it's a typical, I would say, academic extravaganza. You know, it's like solving the climate change problem or solving poverty, or, you know, when Miss World says she wants world peace. That's bullshit, because it's not clear what world peace means, and it's not clear what AGI means. So I think what Ted is alluding to here is that let's not get boggled down with things we can't measure, and let's focus on what we can measure. Which brings me to a tangent I want to bring. You know, let's not forget, here at Orange Capital Partners, we're a hedge fund. We invest money and we want to make money. So we're not an academic podcast or something like that. We're not This Week in ML or any of that. We're not, you know, what we're interested in here, the purpose of this podcast is to give people a sense for what it feels like to run a hedge fund. So why are we doing all of this? Well, we're doing all of this, of course, because we want to learn about it, but we also want to try to generalize, actually, from understanding what's going on in CVPR to potentially understanding what's going on in business and in the market. So we're doing the same thing like all these AIs are trying to do, which is generalize, right? What does it mean to be good at something? What does knowledge mean? How does knowledge progress? And then we connect that with, okay, what does knowledge mean for, let's say, new engineering practices? How do new concepts translate into new businesses? What does it take to generate wealth? Those are all generalized ideas that potentially help us make money. This is our strategy. This is the way we work. It's not the way it's supposed to work, meaning there's no such thing as it's supposed to work like this or that. There's a lot of different people in the hedge fund industry. They do different things. We just do that, okay? And again, for anybody who has other ideas about how to run their hedge fund, please go ahead and do it. Let me know if it works, and hopefully we can inspire you here to think about things a little bit differently. That's the way we think about it. So why are we doing all this? Because we want to tie it to our positions. Tesla is our largest position, NVIDIA our second largest position, and we are interested in the idea of foundation models for decision-making, for embodied decision-making agents, because we think robotics is the next frontier, and wealth can be generated in massive terms with robotics. The key concept of Tesla is that Tesla has been able to create an internet of driving data. And that because of that, they are able to use what's called inverse reinforcement learning, which simply means that since we don't know the reward function of driving, since we can't evaluate what it actually means to do good driving, well, one way to do it is to just watch humans, how they do it, and then infer from there what a reward function would look like. A reward function just means, how do we know when somebody does something right versus something wrong, right? Imagine if you had to infer a reward function from your cat, okay? How do you know when you're doing something that your cat likes versus you doing something that your cat doesn't like? You can't talk to the animal. You can't really have a communication. I mean, you can in certain ways, but you know, it's hard. Well, one way to do it is just to observe the cat and then infer indirectly. That's why it's called inverse reinforcement learning. And now imagine you were programming a robot that is supposed to be sort of friendly to your cat. You could then train your robot through that reward function that you got through inverse reinforcement learning. Just observing your cat, you can then train your robot, and then that robot could hopefully be a nice companion to your cat. So that's the idea of inverse reinforcement learning. And I just want to reiterate the importance of Tesla having this data set that they have, which they built over the last 6 years, millions and millions of miles driven, it's not the end of the road. I think Tesla is just at the beginning. There's a lot of foundation model work that they can do that hopefully they are doing. And tokenization and like I said, tokenizing space, which means tokenizing space and action, and then working with that. There's a lot of work to be done, but they have a data set that nobody else has. And that's unbelievably important. And in my opinion, it is the gateway to $1 trillion market cap company. And it will also help on the robot. By the way, this is not investment advice. Please do your own work. I shouldn't be mentioning these types of numbers. But what I'm trying to say here is that we believe that this is the value creation that Tesla can make because of the data set and all the other things that they need to be solving, you know, from actuators to mechatronics to training and chip design and inference chips and all that kind of stuff needs to be solved also, but the data set is key. Just as a tangent, my son is doing a project where he's working on identifying exoplanets and using AI for that, you know, vision. And look, it's fundamentally, the question is the same thing. Well, what data are you going to train this thing on? I mean, I think building a model that can identify exoplanets is probably not the hardest thing in the world. A high school kid can do that. But the problem is, what data are you going to use this on? Now, not NASA is working with NASA here. He's not working for NASA or anything like that. He's not that kind of person. He's not, you know, Sheldon. but you know, NASA is helping high school kids to get acquainted with astrophysics, and he's interested in astrophysics and all that stuff. So they're going to give him the data, but have they really thought about what kind of data they're giving him? Have they really evaluated different data strategies and then found models that fit? But have they done some sort of chinchilla analysis? I assume they haven't. That's fine. They're astrophysicists. I think that's just, again, that's a tangent for the physicists of tomorrow. Think about these things. It's going to be incredibly important for your career. So back to this episode. As a summary, I think Xiao's presentation, very inspiring, talking about the 3 big pillars of foundation models for embodied decision-making agents. Number 1, foundation model architecture, which means tokenizing space and actions. Number 2, finding the right data strategy, also having, for example, synthetic data, simulation data, all these things. And then 3rd, also the evaluation problem needs to be solved. Okay, what is it exactly we're evaluating? How do we decide we're doing a good job versus a bad job? Thank you.